So I'd like to have a focus on large language models in particular. So the technology that powers typically ChatGPT and other chatbots like this, because also it highlights the technology of neural networks that are behind a lot of what we call AI systems nowadays. Before we begin, a little disclaimer, I'm definitely not an expert in AI or deep learning or machine learning. And actually, that's kind of the point I want to make as well, is that you don't need to be an expert in those technologies, but as developers, it is important to at least get familiar with it and understand a little bit more about these black box technologies and how they can impact our life as a developers and the risks that possibly they can carry and what we can do about them. So large language models, they're, as the name implies, a language model. So a language model is basically a map of probabilities of text sequences so that such a model can predict text sequences when given some input text. The key features of these large language models are familiar to everybody, I guess. They are very good at generating plausible text that human would be able to write typically. And they achieve this by having a very good context awareness when they understand the input text that they receive. When we say large language model, we are talking about the scale of those models, which is growing very fast compared to 20 years ago, when the same technology was possible, but not really used. These scales are measured generally in what are called parameters. We are going to talk about what those parameters represent a little bit. We have some numbers here on the screen. So for instance, GPT-3 is quoted at 175 billion parameters. That's a lot. The other language models that are displayed here also have similar scales in terms of parameters. Okay, so what are the risks? What intuitively do we see as risk when using those language models? Many of those risks are already known if you have heard the news, if you have played with those language models, if you have interacted with ChatGPT. You know about the bias that they can show in the output that they provide. You know that they can produce dangerous output, hate speech, unlawful suggestions. They can give you instructions to craft illegal substances. They could be tricked into providing instructions to build weapons. And of course, there's the class of hallucinations that is very well known, where the model will produce facts and state very convincingly that those facts are correct, when actually they're completely false and totally invented. To understand how that is possible, we have to dive a little bit into how the technology works. Directly looking at ChatGPT is very complicated because it is a very complex model, and other large language models are quite complicated. But we can first look at the simplest form of component that we find in this model, and that is a neural network. So here is what would be typically called a feed-forward neural network, which is the kind of the plain vanilla form of neural network. If you're not familiar with this, they can be depicted as a graph, as here on the screen, made of nodes that are the neurons and edges connecting them. A feed-forward neural network has a direction. So here you see that the information is going to flow from the left, entering the input layer. That will then forward the information in a fully connected manner to the next layer. So not all the edges are visible here on the slide, but each neuron, each node in one layer is fully connected to all the nodes in the next layer. And so from layer to layer, the information is going to flow forward until it reaches the output layer. So that's basically what a neural network is. And each node is going to make a small computation and provide the result of this computation to the next layer. The number of nodes, of neurons that you find in each layer is not fixed. It is totally flexible. It depends on what you're doing. The input layer will typically have a number of neurons that corresponds to what kind of input you want to feed into the network. The output layer is going to have a number of neurons that corresponds to what sort of output you expect. And then there can be a variable number of neurons in each of the layers and a variable number of layers as well. That is typically referred to as the depth of the neural network. So when we talk about deep learning and deep networks, we're talking about such networks where there are lots of hidden layers in between the input and the output layer. So what can you solve what class of problems can you solve with such a neural network? The classical example that is used when introducing neural networks is the recognition of images. For instance, here we have a picture, a low resolution scan of a handwritten digit. And the problem would be to recognize what digits this represents and do this reliably over a large number of handwritten digits. If you were to sit down and write a program to implement this as an analytical solution, it would be quite hard, right? It's not easy to solve this problem in a generic manner. But it is actually something that neural networks are very good at doing. If we wanted to implement a solution for this, this is what it could look like. So we have a neural network. Here we have two hidden layers. The first input layer, the input layer, is going to have 784 neurons. And why is that? It's because we're considering for input these images of 28 by 28 pixels. So that's 748 values. If we consider that each pixel is a single value between 0 and 1, representing the grayscale value of that pixel. So it's very easy. The input layer is going to have as a value all the individual values of the pixels. Then how is the information fed forward through the network? Each of these edges that are connecting a neuron to the next layer will carry little weights. Basically, it's a multiplier. So the result, the contribution from one neuron to the next layer is going to be multiplied by this small multiplier. And then the neurons in the next layer are going to have a small number attached to them called a bias. And the neuron will perform a small function that computes the weighted sum of the activation value, so the value of the neurons from the previous layer, multiplied each by their corresponding weight, the edge connecting to the next neuron, and then added with the bias of the target neuron, then passed through a small function. That function, it doesn't really matter here, it's a nonlinear function that kind of acts as a threshold so that the network isn't fully linear. It's a nonlinear function. For instance, it could be a max function between 0 and the actual value coming from the previous neurons, so that negative values are completely silenced and the neuron doesn't produce any value up to a certain threshold, and that threshold would typically be the bias that the neuron carries. It doesn't really matter here, the formula. What matters is to understand that this is basically a series of calculations that can be done in a vectorized manner, so we can consider the weights and the biases of the network as a matrix of values and a vector of values, and the input is a vector of values, and the whole computation accomplished by the network can be performed as a series of very simple mathematical operations over matrices and vectors that are very easy to do in parallel on massive GPU-based architecture. So that is very easy to scale. Then the same process is going to repeat for every neuron in every layer up to the output layer where we will get the answer. Initially, of course, if we do this, what are we going to use for the weights and biases that we initialize our network to? Well, that's the thing, is that such a neural network is initially completely dumb and will produce garbage, and you have to train it by feeding a lot of input to it, looking at what is the output, and then correcting that input bit by bit until you can fine-tune the different weights of the network. So typically this is done by having a cost function that computes the average error for all the images in our training set. So we will take 50,000 handwritten images like this. where we already know what is the output. So we use a training set for that, and there are many open source training sets like this that you could use if you wanted to implement this. It's actually pretty easy and a good exercise if you are interested in this topic. And so once we have passed all our training set, we can compute the average cost for this pass. And through a mathematical operation, we are going to implement backpropagation and essentially take this error and translate that into small tweaks that we are going to apply to each of the weights and biases in the network. This is technically called a gradient descent, where we are essentially computing what is the slope of the error function around the place where we are currently with the parameters the way they are. And we are trying to kind of roll the ball. Here the picture is like, imagine that the function is in 3 dimensions because there are only 3 parameters. So you have this shape of the function, and you want to roll the ball down a hill until you reach kind of the bottom of the pit, which is like a minimum of the error, which means that our network is very close to an optimal solution, at least a local optimal solution to implement a good output, to produce a good output. And so with our example network here, we would be able to achieve 96.7% success rate after a certain time of training. And this is based on human tests. We know that actually 96% of success rate is very good, because most humans cannot do much better than this, or even reach 100% because of the very bad shapes of some of these numbers. And so we have here a neural network that has, in our example, the 2 hidden layers were 16 neurons each. And so if we multiply the number of neurons in each layer, we get the number of weights plus the number of biases that are attached to each neuron. That's actually 13,002 parameters. So this gives you the scale of what this network represents. Okay, so now we have some idea of how it works in practice to use such a neural network and to construct it. But now we might be wondering, why does it work? How come this structure is able to produce a correct output? And technically, from a mathematical point of view, the network implements a nonlinear regression, so it's able to find an approximation for a function that would be the perfect function mapping the different kinds of input to the expected output. It's kind of building slowly an approximation that is more or less good, depending on which local minimum we are going to reach. But you could also intuitively think about, okay, what this neural network is detecting features in my input. So here on the right, you see these input digits in white. Actually, the first layer of neuron, based on the input pixel values that it received, it could detect some patterns like little circles in certain positions or little bars, and pass this information that they are present to the next layer, the second hidden layer, could combine this and say, okay, so we have a circle here and a bar here. This possibly might be a 9, and so on. That could be a good interpretation of what the network would do, except that in many cases in practice, that's absolutely not what the network is doing. So people have, of course, tried to determine if that is a correct interpretation and play with the input and see if, okay, if this was done based on feature detection, this neuron or this neuron would be turning on and activating highly with this given input, and it's absolutely not what they have found. But it is possible that the network reached a local minimum that is not as good as what the proper feature detection would do, but still kind of works. So in summary, for those neural networks, we know what they can accomplish. We know that they have lots of parameters, and we know that if we wanted to assign manually all these 13,000 parameters, and let alone a model like GPT where you have 175 billion parameters and you need to fine-tune each of them, it's definitely impossible to do that manually, and also very hard to analyze this structure once it's been trained and to predict what the output of the network would be. Edo. So this gives us a good feeling of why such a system could be exhibiting biases and the kind of issues we were looking at for our large language models. So what about GPT then? GPT, we don't have to look at all of the details, but it's basically a much larger language model that has been invented based on the transformer model, a new type of model that was introduced around 2017 thanks to a landmark paper by Google called Attention is all you need. But it's basically just a pipeline of different types of neural networks processing some input to predict a given output. We can have a simple view of the pipeline here. So it's a bit similar to our simple example for image recognition, except here the input will be the text that the user is typing, and the output should be what is the next word that the network, that the language model is predicting. And if you can predict the next word, then of course you can repeat this process and you put it back into the input and you predict the next word and the next word and the next word. And so of course you can generate text in this manner. Of course there are issues with the implementation of this. We need to implement it based on those massively parallelized computations with matrices and vectors. So first, of course, we will need to turn our input text into numbers. And the way this is done is by doing an embedding. So the text is tokenized, kind of cut in small words or subparts of words. And each of these tokens is going to be represented by a high dimension vector. For GPT, I think those vectors have like 12,000 dimensions. So it's a huge vector that represents one token. But initially, these tokens are pretty dumb. They just represent the token without any context. Like if the input text is large language model, the model token, the word representing model, doesn't know what kind of model it's talking about. Is it a fashion model? Is it a mathematical model? It doesn't know. It's just an unqualified token. And it will be the role of the next layers, composed of two blocks, the attention and the prediction layer. It's here depicted as a FNN, which is the abbreviation for a feed-forward neural network. It's very similar to the network we talked about before, except it's in much higher dimensions. So the attention block is going to embed some context, try to have the tokens talk to each other in order to bake more context into each of these vectors. So you can think of them as being like arrows in a massively dimensional space, and the arrows are going to be moved around by the context of the other tokens. So typically our large language model input, the model token is going to be modified by the large and the language words that come before, and that's going to change their meaning to become contextual. And then the role of the feed-forward neural network will be simply to predict, just by training, what should be the next word when we have these contextualized tokens before. And in the GPT pipeline, GPT-3, I think there were 96 repeated iterations of these two blocks of attention and prediction. And then at the end, you come up with a probability of what should be the next token. You select one of them and you unembed it, so you transform that token in 12,000 dimensions, that vector in 12,000 dimensions into a word that is the next word that is predicted. So you see, it's all based on this same context that we were talking about a minute ago, the neural network. Okay, so now we get a sense of what is happening and what can we do about these risks that we were talking about before. How do we mitigate these risks of hallucination, unlawful suggestion? How can we reduce the chance of this output being produced? There are two techniques that the developers of large language models are using in general. The first one happens during training. When you train the network, when you have a massive number of parameters, like 175 billion parameters, you need a much higher number of training data. You need the training data to scale much higher than the number of parameters that you need to train. So of course, we don't have supervised training data at those scales. We don't have like big dictionaries with 500,000 billions of text and labeled predicted output. So what the network is trained upon is by feeding a lot of text into it, and it is self-learning, self-training. Basically, when it sees the full sentence from an article of Wikipedia, it's going to play the game of predicting the next word in each sentence and then correcting by actually processing the next word that was really in the article, and so on and so on. And so it gets better at generating the same kind of text that Wikipedia contains, that the New York Times website contains, and so on. So that's actually during this step that we are introducing bias in the model, because of course this text is biased and all the training data that we can feed into it contains some human bias that is more or less desirable. So then the way to reduce this bias and to improve the kind of output we are getting from this model is by doing supervised learning, where after training with the first pass, now we are giving some example conversations that we want the system to have. And the system is going to produce a few possible outputs with different probabilities, and we are going to rate these outputs from best to worst, and that will feed into the network again with an error function that allows us to fine-tune the parameters and train further the system. And so by doing this, we are training the network, training the model to produce better quality output and to be less likely to produce bad output. The problem is that you cannot do that at 100%, because if you make the network become, the model be so careful, at some point it's going to stop answering. It's going to refuse answering questions by thinking that they are dangerous. So you cannot go too far in this training. So another protection is necessary, and this is generally implemented during the inference phase. So when you are actually executing the network to produce output when the users are using it. And so the first step is going to be prompt engineering. So what the user is typing is going to be augmented with some introduction, telling the model that it is a nice chatbot assistant and it's supposed to produce helpful output for the following user query, and then the user query is there. And possibly it can also be augmented with, oh, and by the way, model, here is the reminder of the rules that you're supposed to follow when you are answering this question. So this is fed into the network to hopefully produce a good output, but even this is not safe enough. So at the output phase, we are going to have an extra filtering system that will look at the output that was produced by the network, because it's very hard to predict what it's actually going to be, and verify that it is safe. And this can be done by possibly another language model that will be very good at recognizing bad input. And maybe it's going to work along with some policies and to combine the two to decide whether the output is acceptable or not. Of course, people have found a way to bypass these protections. And there is a whole class of attacks that are being experimented and really executed on large language models. Of course, playing with the prompt is the most obvious one. So there are what's so-called jailbreaks, where attackers will be able to provide instructions to the model that will disable all the protections and make the model forget all these precautions that were baked into it, or the extra instructions that were given in the input. Of course, this is not desirable, so there are different techniques to prevent it. There are other classes of attacks. You can also attack the large language model during the training phase, and some people have experimented with this by feeding special training data, like data poisoning by inserting some specific documents in it. They are able, even with a small set of dangerous data, they are able to really influence what the network is going to produce. And there are also possibilities of introducing backdoors. So you could, for instance, have a trigger word that is specific, and when this trigger word is found in the input, it's going to produce a different kind of output. So there are lots of possibilities like that, because again, the network isn't like really applying any domain rules. It's just processing output and processing input and producing output that it's hard to predict. You can also trick the network into revealing data. Of course, in the training data, there could be some personal information like emails, phone numbers, and it may be possible to reconstruct this with a proper prompt and disclose some private information that shouldn't be disclosed. Or you can even, it could be a problem that you are able to have the network, the model produce some of the training data just verbatim. If you take ChatGPT and you type as the prompt chapter 1 Alice, and that's it, it's going to produce the first chapter of Alice in Wonderland. So this is the kind of way the network can be tricked into producing almost identical values that were in the training set. And so, of course, there are other workarounds that developers are implementing to kind of block these kinds of attacks. So this is one side of the issue, is how these models can be attacked. Then there is the other side, how you can use those models to attack other systems. And of course, people have tried that, and among the vast spectrum of cyber attacks that you can kind of see here on the screen, all the boxes that are highlighted are attacks that have been conducted with the assistance of large language models. And of course, there are attacks based on generating text, like phishing attacks, where the network will be very helpful to make your phishing emails look better with less typos and everything. But it's also very good at generating code, so it could generate exploits. Typically, ChatGPT is very good at parsing code and finding vulnerabilities in the code as well, so it could be helpful for that. And even if there are protections baked into the model, as the kind of protections we were talking about in a minute ago, people, of course, have created their own like jailbreak versions of GPT. You may have heard of Fraud GPT, Worm GPT. Of course, the dark web is full of people offering different variations of these models. And anyway, the technology is open. Anybody could do that. There are many open source models that you can download, and it's actually very helpful when you want to do some good stuff with it, but obviously you can do bad stuff. And the final thing that I wanted to talk about today is that, of course, those language models will be integrated into apps. That's definitely an important point for developers. And obviously, when you use a large language model like this as part of your app, it is still vulnerable to all these issues that the model is vulnerable to, except now it's going to be through your app. And so typically, it could produce bad output for some of your users. It could disclose some data that was in the training data. If it's a custom training data set, that could be a problem for you. Of course, if you take the output coming from the model, then you have to sanitize it because it's totally untrusted because of these issues and because it's unpredictable. So you have to sanitize it properly and be cautious what you are doing with it. And another point that could be relevant is data protection issues. Sometimes you will want to not have your own local network because those are very expensive to train. Some of the larger models like GPT take actually weeks or months to train over massive infrastructure, so you can hardly have that of your own. But you can use them through APIs. And of course, when you are using them through APIs, you're giving some input to the network and to the model. And what does it do with this input? For instance, OpenAI and GPT, they have different policies depending on the kind of subscriptions that you have. If you are using a personal account, they state very clearly that they are going to use all your conversations to train their model further. So who knows, maybe your your data that you are feeding to the network is going to be part of the training data and may be disclosed later in a future version of the model. So you have to be careful about that. For OpenAI, I think the enterprise level subscriptions and team subscriptions offer this protection where they guarantee that they won't use your input as part of the training data. But it's going to be more and more the case that every big company wants to train those large models. Meta is now asking users of its product to grant the permission of training their models on all the posts and images that you are posting, because they're going to be very hungry for data. So these are a lot of aspects that might be good to keep in mind. To finish, I have a few references if you are really interested in those topics. There are lots of very good books and websites and presentations that you can use. An excellent one is the 3 Blue 1 Brown channel that has an excellent visual explanation of how these models work and how GPT specifically is working and what the attention mechanism actually does. So it's really, really worth your time. There are open source books, like the Dive into Deep Learning book that is used by hundreds of universities all over the world for students that are being taught about neural networks. And it's totally open source, and it comes with code samples, so you can actually build your own language model as you go. And there are lots of other resources like this. So I guess that's it for me. Presentation for Antoine. Thank you.